Today I'm continuing a video that I actually filmed over a year ago, which was an attempted repair on this board. This is a Coco 3 motherboard. It's relatively rare, relatively valuable, I mean, in the grand scheme of things. So I want to fix it, but unfortunately it's been a bit of a challenge and not really a priority, so I haven't really worked on it too much. We'll start by testing the power supply. AC power comes in through this connector here, and then it goes into these diodes here, which are half of a full wave bridge, and then these other two diodes here, which are the other half of the full wave bridge. So if we measure off of one side of those diodes, we get 10.9 volts on this side, and then on this side here we get ourselves minus negative 12.58 volts. So we've got our positive voltage supply and we've got our negative voltage supply on both points here. These go into this chip, which is the main regulator chip. So we will have inputs on pin 16 and pin 15. So again, on pin 16 we've got 10.94 volts, and on pin 15 we should have negative 12 volts here. We got negative 12.5 volts. This chip requires negative 12 volts because it implements part of the RS-232 interface, and the actual RS-232 standard states that there must be negative voltage for part of the signal. So it uses that negative 12 volts in order to build standards compliant RS-232, which is surprising because the serial port on the Coco doesn't have a proper UART or anything like that, so it's all software controlled anyways. So for them to build a standards compliant interface and then not have hardware to do proper RS-232 is kind of a weird decision, but whatever, who am I to judge? So we have our voltages here. We will have on pin 3 of this chip 5 volts, pretty close to it. And yeah, if we measure it, we look at it, oh, it's 5.07 volts. So that's, definitely there. And, it's sitting stable at 5.0775 volts and, staying pretty stable there. So it doesn't look like we've got a big problem with the power supply. It seems like this power supply is working. Now that we've looked at the power supply, we can take a look at the RAM chips. The Coco uses 4 64K by 4-bit chips to make up 128K by 8 bits. So there's two banks. Basically, I think this is bank 1 and this is bank 0. In bank 1 you have your odd numbered addresses, and bank 0 you have your even numbered addresses, or vice versa. To test these chips, what we need to do is take a look at the input address lines and see if they're pulsing at all. And there's the input, and we get it. There's a digital signal on there. And then we also look at the output data lines. So there's 4 data lines on this chip. So I'll pick one of those data lines, and you can see there's output on that chip. So it is outputting, some sort of data based on the input addresses that are being provided to it. So that tells us that chip is good. This one, we've got an input here. Let's take a look at the output. Yeah, there's output, so it looks okay. Can't really tell what the data is, but we can see it's a digital signal and it looks sane, although that one's pretty noisy. A lot of strange signal there. Then here, and we've got some signals here. So it looks like these chips are probably okay. Now that we've tested the RAM chips, we can test the buffer chips that interface the RAM chips with the rest of the system. So there's two 74LS244s, which are standard buffers. These are used for writing data into RAM, so there's one for each bank. And then we have a 74LS374, which is a latching buffer. This is used for reading data from RAM. And then there's a 74LS244 also, which is also used for reading data from RAM. I can test these two buffers by looking at pin 1 for the write enable signal. So what happens is the gimme generates this write enable signal, and it goes back and forth between bank 0 and bank 1. So let's just take a quick look, see if we've got anything here. And we had something. We had something shortly. Did you see that? That just at the front of the scope there, the signal goes down for a second and then it goes off. So that's telling me there's something odd happening. I'll take a look at the other chip here at the write enable on that chip. And we get the same sort of behavior. It's going down and then it just sits at, well, let's adjust the scope here. I think it's sitting at 5 volts. Yeah, it's sitting high at 5 volts. Drop for a little bit and then it's high at 5 volts. Likewise, you know, oh, that one's not doing it right now. But that's not right at all, because both of these write enables, they need to go low for this chip to be active. So there's an issue. It appears with the write enable line. So I'm not even going to bother testing these two chips. I will, you know, just pulse these, take a look, see what we've got. Looks like we've got some random digital data on these buffers, but you know, a critical thing is going to be this write enable. That's just sitting there high. Now that I tested the buffer chips there, I'm going to just do a one quick test of the keyboard connector. So pins 8 through 16, they will strobe in sequence. So I think, you know, they're going to go this way, strobing continuously. They're basically being pulled low in sequence. So if I put the scope on one of those pins, I should see it go low momentarily, and it doesn't. Now, the interesting thing about this part of the system is that this is all software controlled. So if you're getting a keyboard strobe, then you know that the CPU is running, and you know that your PIA is also working, your keyboard PIA. So, you know, I can tell you right now, the CPU is not running at all, which, based on the fact that there's a problem with the RAM write enable, you know, this is a good hint that the CPU is, you know, certainly not running at this point. Next thing we could do is check some of the test points on the board. So let's check the Q and the E clock. So the E clock is test point 2. And as you can see, we've got a good digital signal there. And the Q clock is test point 3, again, a good digital signal. These two clocks, I believe the Q clock follows the E clock. If I suspected a problem with these clocks, I would actually connect 2 probes up to those clocks and then check to see if they were properly out of phase, but I don't think that's a problem, so I'm not going to go there quite yet. The next test point that I'm going to test is TP4, which is the RAS signal. This is the row address strobe. This goes to the RAM chips and it basically selects the row that you want to read or write to. So it's just a clock signal to select the row. Now on a RAM chip, there's a grid of addresses, and basically it's a row and a column. And when you go into row mode and you put an address into the 8 address lines, it selects that row. And then almost immediately after, you check the CAS line, which is column address select, or column address strobe, sorry. And that's this one right here. It's test point 5. So let's take a look at this here. And our column address select is good as well. So we've got a row address and a column address being generated fine. That is generated from the gimme, so that's working okay. The E and the Q clock are also generated by the gimme, and that's okay. So let's take a look at the video signal here. And, you know, that's no video signal. I'm going to switch this to AC, crank the sensitivity up a bit, and looking at it, that's definitely not a composite signal. That's not a valid composite signal at all. So it's kind of interesting that we have a good Q and E clock coming out of the gimme, We've got a good CAS and RAS signal coming out of the gimme. We have a bad video out, and we also have a bad write enable out. I'm going to do one quick test here on the gimme itself, just in case the write enable lines are shorted or something like that, or there's some problem, let's say, on those lines. And I'm just going to test it straight from the gimme. Crank this thing back up again. Let's acquire a good signal and set the scope accordingly. And then let's test the gimme here. And there's nothing on there. Oh, it's AC coupled. Don't do that. Put that there. And we just got a solid 5 volts. It's just constantly high. It's not going low. I mean, it flashes a fraction, but that's it. So there's obviously something wrong there. A possible way I could eliminate issues is I could pull, say, this buffer chip. Let's try to pull it out and see what we get. Use my hand there. Okay, buffer chip is out. And then we will test signal there. And no, it just stays high. So it's not the buffer chip at all. The problem is in the gimme. It's gotta be. At the bottom of the board, there's a couple of inverters that are used for different purposes. And one of them, IC15, has the V-Sync and H-Sync video signals in it. So let's just take a quick look and see if those are being generated. So this is the V-Sync, and as you can see, yeah, we're getting a signal there on V-Sync. So the gimme's generating V-Sync, and if I go 8, 9, 10, 11, that should be my H-Sync, and likewise H-Sync. So part of the video signal is being generated by the gimme. Now that I've done testing with the multimeter and with the oscilloscope, I am going to take out the logic analyzer, which is the next tool in my arsenal, to test this thing out. The logic analyzer is going to let me take a look and see if the CPU is actually working in a proper manner. So I can actually look at the address lines and the data lines on the board and see what's happening there and just get an idea. So what I'll do is I'll look for the CPU booting up, and we'll see if it's loading the code, the correct code, and we'll go from there. Okay, so the first thing that happens when the 6809 fires up is it looks at the top address in memory, and it pulls that and it uses that as a start vector, which it jumps to. So we're going to see the CPU, if it works, pull the address 8C1B from memory. We're going to see it jump to this location, and we're going to see it execute this ORCC hex 50. ORCC hex 50 is going to disable IRQs, so it's basically the init routines here. And then the next thing it does is it pulls some basic configuration variables for the gimme. So this load A, MC3, and MC1, those are gimme initialization variables. And then it is going to store that in init0, which is address FF90, which is the initialization address for the gimme. It's the initialization port. So if we see this in our extract from the logic analyzer, that's going to mean the CPU is working to some degree, and it's also going to mean that the ROM chip is working as well. In order to do this, there's a couple ways that you can connect up a logic analyzer. So one option is I could, on these pins here on the CPU, I could use mini clips in order to connect up. Problem is when you're doing 24 lines, you end up with like clips all over the place. So I built a little breakout board that plugs into the cartridge slot that basically has a bunch of headers there for the address lines right there. Those are all address lines. And HP has a funky little system that allows you to do a header directly into their logic analyzer sets. So it's just a little breakout board that allows me to test this better. what I need to do is I need to trigger off of the 8C1B, which will appear on the address line. And when that trigger occurs, the logic analyzer is going to record 2K before that trigger and 2K after that trigger. This will allow us to analyze what the addresses are switching to on the Coco bus so we can see what's going on. So we've got that set up, and I think we can go to list and let's arm it, and we'll fire the Coco up and see what happens. Okay, so we fired it up. It captured the signals, and you can see here if we go back in time, the bus starts at FFFE, which is what it's supposed to do when the 6809 powers up. It goes right to the top of memory. Eventually, it finds some data and it switches over to FFFF to get the second 8 bits of the start vector. So it does that, it gets the 2 addresses, and you can see then it jumps to 8C1B here, and we scroll down 8C1C, 1D, 1E. We can see it's going through memory one instruction at a time. 8C20, sorry, and then 8C21. Then we see this weird thing, which is an FFFF. What that means is that the CPU has gone into tri-state mode. All of the address lines on the CPU are tied high. So when the CPU is not using the address lines at all, it will go high for all the address lines, and you can see that happening there. So it's not actually the CPU saying, hey, go to FFFF. It's actually just tri-stated. Okay, so the next thing on the address lines after this FFFF is FF90. Now that is our gimme initialization register, and that means that basically the CPU has pulled that register from the ROM, and then it's run enough code to, you know, get to this point in the execution, and it's going to write some data to FF90 and keep running along at 8C22, 8C33, etc., etc., etc. This shows us the CPU is working. This also shows us the ROM chip's working. So based on everything that we've looked at so far, you know, we had signals going across all over the place. We had, you know, memory outputting data. The power supply is powering correctly. CPU and the ROM are working correctly. The only thing left at this point has got to be the gimme chip, which means it's probably toast. So what I'm going to do is I'll pull the gimme chip out and pop it into a known working board and see if that unit boots up, and if it does, then we have another problem, but it's likely that it won't. Okay, I've done a lot of testing on the board itself, and I'm kind of thinking that this gimme is probably not completely internally shorted. I have another Coco board, so I could put this gimme on there and test and see whether it's working or not. So I'm going to do that. I'm going to pull this thing out, and you know, this isn't really the ultimate repair procedure because there's some risk that this gimme could take out my other working motherboard, but I've done all these tests and I feel that it's a low risk. So to pull these out, you know, don't do what I'm doing here using a jeweler's screwdriver. Get the proper removal tool. You can basically break this socket really easily. I'm impatient and I don't want to wait for, you know, someone to send it to me if I order it, so I'm just going to pull this thing out, and you got to be really careful. You can cause all sorts of damage. Just do this, ease it out one side at a time, and the gimme is out. So let's try this on another board and see what happens. So I've got the gimme in the known working board, and we'll try powering it up, see what happens, and nothing. No, we just have the same symptoms that we had before on the bad board. So it looks like this gimme is actually dead. It wasn't a complete waste of time trying to analyze everything before plugging it into the known good board, because there's that chance that the gimme could take out the known good board. So I think it was worthwhile, but at the same time, we've identified our problem, which is the gimme, which is basically unattainable. So this board is not really repairable. Okay, the last test that I'm going to do is to make sure that the known good board still works after that test. you know, there's some risk that I put this gimme chip in and then it could take out other components in the known good board, which would be really bad. So I've put the known good gimme back in that board, and we'll power it up and see what happens. And she powers up just fine. What can I say? That gimme is dead. Not much I can do to fix it. The only options that I'm going to have for that board are to, you know, either do a custom build of an FPGA, which seems like a lot of work. In fact, it is a lot of work. Option B is that I could maybe wire up some custom 7.4 series logic to, you know, build a basic memory controller that would allow me to have, you know, a computer with a console only output, so no video at all, but, you know, I could load up BBS programs and stuff through the serial. I'm not sure what I'll do. Maybe I'll just put that board, you know, on the wall next to the other one I blew up. Well, thanks a lot for watching. I hope you learned something from my video, and, you know, if you enjoy what I'm doing, please subscribe. Check on that you know, subscribe button below. It really helps out a lot, and I hope to see you again soon. Thanks for watching.